Linear transformations are the important functions in linear algebra. In a previous video, I've showed you some examples, for instance, rotations and reflections. So these are examples of geometric origin. And so there is a connection between linear transformations and geometry. But the definition of linear transformations is purely algebraic. First, there is the axiomatic definition that tells you that a linear transformation is some function between Rn and Rm that satisfies a couple of properties. The second definition tells you that a linear transformation is given by just a matrix. So the transformation will send a vector v to A times v. And there's a term that says that both of these definitions are equivalent. So if you have a linear transformation in the first sense, you can find a matrix A for which the transformation is given by the formula T of V is equal to A times V. And vice versa, such a formula defines a linear transformation, so a function that satisfies those two axioms, which I will write in a moment. So it's important to know both definitions, okay? And the second one is maybe the more practical one, where you have that you have the explicit matrix that gives you the linear transformation, but not every linear transformation is given right away by a matrix. For instance, if you look at orthogonal projections, so these are also linear transformations, and if you want to write down the formula, well, it will involve the dot product. You will not see any matrix right away. But to see that it is linear, well, you have to use the first axiomatic definition. So it's important to get used to that definition. Also, if you take more advanced courses in mathematics, and particularly in algebra, you will see again more definitions where we say we define something in terms of a list of properties called axioms. So let me repeat that definition. So T, so a linear transformation from Rn to Rm. Okay, so a function. So first of all, right, it is a function, so it will take a vector to a vector. We have a notion of function between two sets. A function from the first set to the second set will take elements of the first set, and it assigns to it elements of the second set. So this is what is a function in general. Okay, so it's not always given by some formula f of x equals some other something else. I mean, this what you see in calculus, this works well when you are working with numbers. Okay, f of x equals cosine of exponential of x, etc. Okay, but there's a general notion of function, first of all, that says that that assigns you have a function between two sets, and it assigns to element of the first set a unique element of the second set. Okay, and here we are in linear algebra, so those sets that we look at are actually sets of vectors. So Rn and Rm, okay, so these can be distinct, and our function sends a vector to another vector. Okay, so if we have so this is notation for a function. So T, right, so maybe I can write this first. So this is a function. So a function from Rn to Rm. Okay, this T is a linear transformation. So maybe I'll write this here. So this T is a linear transformation if it satisfies a couple of properties. All right, so the first one is that if you apply T to two vectors u and v, to the sum of two vectors. So this will be equal to T of u plus T of v. So this is for all vectors uv, and we start from Rn. Okay, so T of u, T of v, they are in Rm. So maybe I should emphasize this. So here, well, we have a total. We have more than just two vectors here. We have u and v, okay, and we have u plus v. So these are all in Rn, and the sum here is also in Rn, right? So u plus v will also be in Rn. So we have like three vectors in Rn, and we apply our function t to these, okay, and we'll get, well, three vectors in Rm. So T of u, all of this is a vector in Rm. All T of v is also a vector in Rm, sorry. Okay, and so is the left-hand side. Of course, so here in this equality, we are actually comparing vectors in Rm. All right, so we start here. N could be 3, and maybe m is 4. So we start with vectors in R3, we apply our linear transformation, and we get vectors in R4, for instance. And we want all these to be equal. Okay, so T of a sum is the sum of the T's. Kind of a short way to remember this. T applied to a sum of vectors is the sum of the images of those vectors under T. Okay, so we want this to always be true. Okay, this is some condition on our function T. And this is, I mean, if you just go back to function and calculus, here you can take R, N and M to be equal to 1. Then you're looking at some function from R to R. And you'll see most functions in calculus don't satisfy this. Okay, so if you take, well, f of x equals x, of course, satisfies this kind of condition. But if you take f of x to be x squared, okay, and here you just take u and v to be numbers, and you take t to be this function f of x equals x squared, you'll see that this equality is not satisfied. Okay. So this is one condition, right? So this is the first condition. The second condition, it has to do with scalar multiplication. So this condition has to do with addition of vectors, right? So what other operation do we have with vectors? Well, we always have scalar multiplication. So the other condition is that if you apply, you can start with your vector v, you can multiply it by some scalar c, okay? So you could first do this, you multiply v by c inside Rn, and then you apply the linear transformation t to end up in Rm. Okay, so we can do this, or what we can do is first apply t to v, we end up in Rm, and in Rm can still multiply, this is still a vector, I can also multiply it by the scalar c. And we want these two to be equal. Okay, so this should be for all vectors v and Rn. Okay, and all scalars c in the real numbers. So, all right, so this is again the axiomatic definition of a linear transformation. I want to look at a couple of examples. Okay, so we'll look at some function given by some explicit formula, and we'll check if it satisfies one of these two conditions. Okay, so one of them will satisfy them, one will not. Okay, so I just need to erase this and then start on a new board.